Welcome. In this session, we learn how to write the equivalent circuits of the elements R, L, and C when we apply the Laplace transform. So how do we write the equivalent of R means the resistor, inductor, and capacitor if we use the Laplace transform? So let's start with the resistor. Suppose we have a resistor. Okay, we know the in time domain, we know how V and I are related. So if I say this is a resistor R, so if the current flowing through this resistor is I of t, and the voltage across this resistor is V of t, then we know from Ohm's law. So using Ohm's law, we know V of t is equal to R I of t. All right, where we assume R is a constant. So if we take the Laplace transform of this expression on both sides, what we'll get? So taking the Laplace transform on both sides, we'll say Laplace transform of V of t is equal to Laplace transform of R I of t. Now, since we don't know what is V of t, so let's assume the Laplace transform of this is simply V of s. So it is V of s. That's equal to, using the properties of Laplace transform, R will come out. So it will be the Laplace transform of I of t. So Laplace transform, again, we don't know what's I of t. So let's assume the Laplace transform is simply I of s. So what we have got, once we use the Laplace transform, we obtain V of s, means the voltage across this resistor in Laplace transform domain is equal to R times the current in the Laplace transform domain. So this is how the voltage and currents are related in Laplace transform domain in the resistor. So if I define what is R from this in Laplace transform domain, it is Vs by Is, right? And we know transformed voltage by transformed current is referred as the impedance. So the impedance offered by this resistor in the Laplace transform domain is again simply R. So the impedance offered by the resistor in both in time domain as well as in Laplace transform domain or the frequency domain is simply R, because we know from this R is simply V of t by I of t. So whether resistor is in time domain or in frequency domain, it remains the same as. Only thing is the voltage and current is changed. Means if it is in time domain, the voltage is V of t. If it is frequency domain or Laplace transform domain, it is simply V of s. Right. So nothing happens to the resistor in this. Right. It is replaced by the same resistance value. So the impedance is simply equal to R. That's the impedance offered by this resistor. Now let's talk about inductor. So if we have an inductor, let's suppose we have an inductor whose inductance is L, and let's suppose the current that's flowing through this is I of t, and the voltage across this inductor is V of t. Then we know in time domain how the voltage and current is related. So we know V of t is equal to L dit by dt. So to obtain the Laplace transform domain expression, means how the voltage and currents are related in Laplace, we'll take the Laplace transform of this expression on both sides. So taking Laplace transform on both sides, we'll have Laplace transform of V of t is equal to Laplace transform of L dit by dt. So again, as we don't know what is V of t equal, so let's assume the V of t as Laplace transform as V of s. Then using the properties of Laplace transform, L will come out from this. So we'll have L Laplace transform of dit by dt. Now we know the Laplace transform of differentiation of a function. We know Laplace transform of, we have Laplace transform of dy by dt, where y is a function of time, means differentiation of y of t is simply s times y of s. What is y of s? Where y of s is simply the Laplace transform of y of t. So y of t is Laplace transform of y of t is y of s minus y of 0. What is y of 0? Y of 0 is the value of y of t when t is equal to 0. It is the initial value of this. This is referred as the initial value of this function y of t. So this is how we write the Laplace transform of a derivative of a function. Now we have derivative of current here. So how do we write the Laplace transform of this? We'd say v of s is equal L. So Laplace transform of dt will be simply I. S times I of s. What is I of s? I of s is the Laplace transform of I of t. Okay, as we don't know what's I of t, so say Laplace transform I of t is I of s minus I of 0. What is I of 0? Value of the current at t equal to 0. So where I of 0 is simply value of I of t when t is equal to 0. So simplifying this little bit, we'll have v of s will be equal to ls times I of s minus L I of 0. So this is the voltage expression of this. So this is how the voltage is related in the frequency domain with the current, right? All right. Now first from this, so this is how the voltage is related to the current from this expression. So this is how the transformer voltage is related to the transformer current. Okay, transformer current means Laplace transform of the current and Laplace transform of the voltage, right? So this is how these are done. Now I'm going to assume initially that let's suppose I of 0 is 0. So from this expression, what we'll get? From this expression, we'll say V of s will be equal to Ls times I of s. Now, what do we write? What do we say V of s by I of s? We say this is the impedance, and impedance is usually rated by Z. And since this is a function of s, so let's Z of s. So the impedance offered by the inductor is simply L of s, and the unit here is ohm, right? So the unit here is ohm. So this is the impedance offered by the inductor in frequency domain or simply Laplace transform domain. So this is the impedance offered by this network of inductor simply. This is how we write the voltage and currents if I of 0 is 0. Now, if I write the equivalent circuit of this inductor in frequency domain, so how do I write that? So we'll say this is an inductor. So inductor will be replaced by Ls, and this is the voltage is simply V of S, and the current flowing through is simply I of S. This is how we replace the inductor. So if the I of 0 is 0, then we'll say the equivalent of the inductor in S domain or Laplace transform domain is simply this network. This is how we replace the inductor with. This is very, very important. So if the initial value of the current is 0, we'll say the inductor gets replaced by this equivalent circuit. Now, if the I of 0 is not equal to 0, if I of 0 is not equal to 0 here, so if we say I of 0 is not equal to 0, then we know the voltage is related to the current by. So we'll say voltage here is related to the current by this quantity minus Li0. Since the left hand side is voltage, so what will be these two quantities? Voltage and voltage, right? We can add apples with apples. We cannot add apples with oranges, right? So the unit of these quantities must be same. Means this must be volts, this must be volts, and this must be volts. So the unit must be same. So if I look at the term. So what is LS? LS is the impedance. We know impedance times current is voltage. So this is current. This is voltage. Now L times I naught of 0 is also a voltage, right? So if I have to draw the equivalent circuit based on this expression, so if I have to draw the equivalent circuit based on this expression, how will I draw that? So I will assume the KVL model, right? So to draw this, that means I have use this different marker. Then I'll say this is LS. Let me use, let's suppose this is LS. Then I have one voltage, which is the value of this is minus. Also, I will write minus on this side, plus on this side. So the value of this is simply L I of 0. And this is the voltage. So if the current flowing here is I of S, then I of S times L of S is this, will give me this, then minus Li of 0. And this should be equal to the V of S. So this is equal to the V of S value, right? So this is equal to the V of S. So this is the equivalent model if I naught of 0 is not equal to 0, right? So this is referred as the voltage model, right? But from this expression, if you look at this expression, I can also write it like this. I can also write current in terms of voltage. So I will say from if I naught of 0 is not equal to 0, from this I will write I of S will be simply equal to, I will take this term on the right hand side and divide both sides by LS. So we'll be left with VS divided by LS plus L and L will cancel. I will be left with I of 0 divided by S. So please check the terms. So this is the current model. So I can also replace this by a current model, right? So if the left hand side is current, what must be these two quantities? These are currents. So these must be currents, right? So Vs divided by Ls is the current. I of 0 divided by S is the current here. So if Vs divided by Is, what was the value? Is impedance. What is 1 by Ls then? So it is called the admittance. So admittance multiplied by voltage we know is current, right? Current is also written as admittance. Admittance is denoted by letter Y times V. So this is the current in terms of admittance. So what is 1 by Ls? It is the admittance, and this is again the current. So I can also draw the model of this, equivalent model of this using this. So I will say this is the incoming currents, and let's suppose these two are outgoing currents. So how I will draw this? Say this is the admittance of this is simply like this. When you multiply this by V of S, that will give you one current, right? Vs times this one by Ls. If you divide by this Ls by this, and we'll have one more current here, and it is outgoing, right? So if this is incoming, let's suppose Is is incoming, Vs divided by Ls is simply this current, and I naught of 0 divided by S is this current. So this current plus this current is equal to I of S. So this is another equivalent model of this. So based on whether I of 0 is 0 or not equal to 0, you can write the three equivalent circuits of this inductor in Laplace transform domain. If the initial value of the current, this is also referred as the initial condition. So if the initial condition, or initial value, if the initial condition our value is 0, then the equivalent of the inductor is simply, you will replace it by Ls. This is important. So if this is equal to 0, then you will replace the inductor by simply Ls. You will replace it by Ls in frequency domain. This is very, very important. But if it is not equal to 0, then you will replace the inductor by either this or this, depending upon which one will give you the easier solution. Okay, so you can either use this one or this one. This is referred as the KVL model, because we have obtained it from this voltage equation, and this is referred as the KCL model, because this we have obtained from this KCL equation, right? Using the current equation, KCL model, right? So these are this equivalent circuits or models of this inductor in Laplace transform domain. Now next we go to the capacitor. So if we have a capacitor, so let's suppose we have a capacitor now. The capacitance is C. The current flowing through is I of t, and voltage across this capacitor is V of t. We know the voltage current relationship in this capacitor is simply given by V of t will be, sorry, I of t will be given by C dVt by dt, right? So to determine the Laplace transform equivalent, taking Laplace transform on both sides, so we'll have Laplace transform of I of t is equal to Laplace transform on the right hand side. So let's suppose the Laplace transform of I of t is I of s, as we don't know what's I of t. So from the properties of Laplace transform, CV is a constant, it will come out. So the Laplace transform of dV by dt. So again, using the Laplace transform of the differentiation of a function, we'll get this. So we'll write I of s will be equal to C. Let's suppose the Laplace transform of V of t is simply V of s. So we can write the Laplace transform of this differentiation as S Vs minus V of 0. What is V of 0? V of 0 is the value of V of t at t equal to 0. So this is equal to Cs times Vs minus C V naught. All right. So this is the current voltage relationship in capacitor in Laplace transform domain, right? So this is the current voltage relationship in Laplace transform domain. All right. Now again, if we say V naught of 0 means the initial value of this voltage at t equal to 0 is 0. So what do we get from this? We say I of s will be equal to Cs times Vs. From this, if I write Vs divided by Is, this is simply 1 by Cs. So that means the impedance offered by the capacitor to the flow of current is simply, so the impedance offered by the capacitor to the flow of current is 1 by Cs. And if I write Is by Vs, so if I write Is means inverse of this, what is inverse of impedance is called admittance. So it will be Cs. So the admittance offered by this capacitor to the flow of current is simply Cs. All right. So this is how we write the equivalent. So if I say V of 0 is 0, so what will be the equivalent model of this capacitor? So we'll say we'll replace the capacitor simply by 1 by Cs if the initial value of this is 0. So this is the current and this is Vs, where Vs is equal to Is times 1 by Cs. So this is the equivalent model. Now if V of 0 is not equal to 0, so what if V of 0 is not equal to 0? So what we'll have? We have I of s is equal to Cs times Vs minus C V naught, right? So if the right hand side of this left hand side of this expression is current, what must be the right hand side? So these two must be representing currents. So these two are current. So that means we know CS is simply the admittance. Admittance times voltage is current. So this first term is the current, but C times V0 is also representing here current. So if we draw the equivalent circuit of this, how do we do that? So we say if this is the capacitor, so this is simply 1 by CS times. So this is the current, but this is minus times. So if I say this is incoming, that means this must be also incoming like this. So this must be the direction of this. So this is V of S. This is I of S. And this is C, V0 of 0. Why is the arrow in the upward direction? Because if I say this is incoming current, these two are outgoing current, but this is minus times. That's why I'm saying this is also actually incoming current, right? So if I take this on this side, this and this are plus, means they are entering this node, and this is the current that is leaving this node, right? All right, so this is the KCL model. So this is based on KCL expression. So this is referred as KCL model, or KCL model based on the KCL equation, right? Now from this I can also write one more, another way to write it. If V0 of 0 is not equal to 0, so I can write it in terms of voltage. I'll say V of S, I will write on one side, and I will take this on the other side. It will be CV0 plus I of S, and I will divide by CS. So it will be IS divided by CS plus C and C will cancel. We will be left with V0 divided by S. So this is the voltage expression. If V0 of 0 is not equal to 0. So this is the voltage expression. So if the left-hand side is voltage, that means these two quantities must be representing voltages. Now we know IS multiplied by 1 by CS. 1 by CS is impedance. Current multiplied by impedance is voltage indeed, right? So voltage is equal to current multiplied by V, right? So this is the voltage. So this one must be also voltage. So based on this, we can draw the equivalent model of this. We can write it like this. So I'll say this. So this is 1 by CS, and this one will be plus, this one will be minus, and this should be equal to V of S. So this is the current flowing through this. Let's say this is I of S, and this is V0 of 0 divided by S. So V of S is current multiplied by this impedance plus V0 of S divided by this. So this is the model based on KVL expression. So you can check it, KVL model. This voltage drop plus the voltage drop that takes place across this impedance is equal to the VS. So these are the equivalent model of capacitor, inductor, and resistor. So if we have to replace this resistor in Laplace transform domain, we will simply replace it by R. So if we have to replace the inductor when the initial value of the current is 0, we simply replace by LS. If the initial value is not equal to 0, we can also replace either this by this model or this model, right? Same way, if we have to replace the capacitor in the frequency domain or draw the equivalent circuit in frequency domain, we simply we replace the capacitor by 1 by CS if the initial value of the voltage across the capacitor is 0. But if initial value of the voltage is not equal to 0, we can either use this model or this model, depending upon which one will give us the easier solution in the model. So what we have learned from this. So what we have learned from this. Right, so if we have an element and we know the VI relationship in time domain and in Laplace domain, what happens to the relationships, right? And what is the impedance offered by these elements? All right, so if I say it is R, element is R, so time domain relationship is V is simply R times I. Okay, so actually it is V of t. So let me use time domain as well. So let me use time as well. R times I of. Now in Laplace transform domain, the expression is simply V of S is equal to R times I of S. So what is the impedance offered by this? Or simply how do you replace this resistor in frequency domain? We simply replace it by R. Okay, so this is the first element, resistor. Now if we have L, so if we have L, we know we are I relationship for L is in time domain L di by dt. In frequency domain, if the initial value of the current is 0, so we'll say if the initial value of the current is 0, if I of 0 is 0, V of S will be simply Ls times I of S. So what's the impedance offered by this element? It is simply Ls. So this is the second element. Now the third element, so is the capacitor. We know the IV relationship of capacitor is C dV by dt. So if V of 0 is equal to 0, means the initial value of the voltage is 0, then I of S, let me write V of S. So V of S is simply I of S divided by C of S. So what is the impedance offered by this? It will be simply 1 by CS. So this is how we replace the elements. So we replace the element R by simply R, inductor by Ls, and capacitor by 1 by CS. This is the equivalent model of these resistor, inductor, and capacitors. All right. So we'll leave this session here. In the next session, we'll solve some examples.